with that, we will now move to the shared perspectives breakout for reality capture and the tolerance dilemma with Brianna and Kelly. Take it away, Brianna.
Awesome. Well, it was another packed discussion diving into layering of tolerances. And the discussion really started because Nathan is letting us use his house as kind of a sample project, and we're looking at how we can use reality capture kind of end to end through the project. And the discussion that we were talking about specifically today is how can we handle all of the different types of tolerances along the project delivery supply chain? I'm not going to get into all the details because Kelly did a fantastic job walking us through some of the things that you can do to help along the way. We had a couple people on the call that are prefabricators that have done this, gone all the way from the first scan all the way to fabricated, 350 foot long pipes and installed them, and had some great lessons learned. You can't scan once at the beginning with a low level accuracy scanner and expect to install prefab at 1/8 of an inch tolerance. So you need to know what is the activity that you're doing, what is the output you need, and what are the tools and checks that you need to make along the way.
Fun times. So the tolerance dilemma, this kind of actually came up when we were talking about Nathan's house. And I think the kind of the way for us to kind of kick this off, I guess, is just hash through kind of the same thing we hashed through then, because I think what surprised Nathan was like the layers of tolerances that exist out on a job site. Particularly when you're working with reality capture. And so I don't know if anybody, this is like supposed to be a roundtable, right? So like, I don't want to make a presentation, right? So let's, do we just want to kind of brainstorm, list them out, talk through them, see if anybody has any questions?
Well, Kelly, we're going to start with the how might we statement. Then we're going to go into a couple of quick intros from some of the team members we have here. And then I'm going to pass the baton for you to dive into layering tolerances. And that's when we can kind of get into the weeds here. But we want to start with the how might we statement. Like we always do, it's how might we understand assumptions and dependencies used to produce as is BIM from reality capture scan data in ways that helps owners select the right tool, activity, and output at the right time so that we can combine value of each use case outweighs the cost to acquire it. So it's important that we kind of set the stage here so that we understand, where we're going with this problem. So now now that we've kind of set the stage, I'm going to pause. We're going to do some participant intros. So with that, I'm going to stop sharing and I'm going to go around the room and we're going to start off with Todd. So Todd, go ahead and introduce yourself with who you're with, where you're from, what you do, and why you're here. What are your expectations?
Okay. All right. Todd Sutton, Zachry Corporation. I'm Senior Manager for Construction Technology, looking at improving the way we do reality capture. And also for this particular session on the tolerances, we're talking about prefabrication, components that are prefabbed off site and to be delivered on site and making sure it fits up with their correct tolerances. So I'm hoping to learn something from this discussion.
Awesome. And go ahead and jump in here, DJ. Same set of questions for you.
Sure. I'm actually on the software side. So I'm currently at Procore as a strategic product consultant. So there's a group of us that came from industry to help support our customers in that. Before that was in the general contractor space, interacting with quite a few here of y'all here. And specifically, we used a lot of laser scanning and 360 photo documentation while I was at Excel and even a little bit at Hazelden before that, and started. First major laser scanning project for me was actually the Texas A&M Stadium renovation. We did a whole bunch of scans for that process. And yes, tolerances and struggle and coordinate alignment and all that other stuff. We got it figured out, but it took us a while.
Awesome. Looking forward to hearing your opinion, having been through it and in the trenches. I don't think Tim's on the call. Tim Jarvie, are you on? Okay, we're going to skip down to Tom Myers.
Tom Myers, Duke Energy, 3D metrology services. We provide it inside within Duke and commercially outside of Duke. Yeah, we have more of an issue that we try to maintain really high precision, and we get a lot of questions about, well, we don't need it all that precise, so could you just do simpler scans? And it's a little difficult for us to really want to lighten up our tolerances, because if they eventually want some aspects to be high precision, we've already gone through and done low quality scans, and then you run into the, well, we'd have to go back and rescan everything. Like so that's one of the bigger aspects for us. Are we recording the breakouts?
Yes, we do record.
Okay.
So
That's all I got.
we can anonymize things or not use project names if needed.
Okay.
Okay, awesome. Thanks for the intro. Next up, we've got Blaine. Go ahead and give it a go.
Blaine Grantham, Titan AEC. And basically I've been working on the scanning side for our business, working with our some of our clients. And tolerance is key for us, especially when we're trying to tie this into construction, because most of the stuff that we do is around design construction. So I'm here to learn. I'm here to provide some pains, maybe even some pains that have been fulfilled or taken away. So that's what I'm here for. I can't wait to hear the conversation with Kelly and these guys.
Awesome. Now we're going to take it to the OG reality capture, Dustin.
Hey everybody. OG, I like it.
OG.
So
Original
I have a
guru.
company called FlywheelAEC, and we do a lot of reality capture and civil BIM. So you'll hear me reference a lot of like infrastructure type of tolerances today probably, but we do some large commercial buildings as well. So a lot of drone aerial mapping with high resolution and accuracy is really what we focus on, as well as laser scanning. And so especially from like a site perspective, where you might have much longer range and different types of control than you typically would inside the building.
And Dustin, you have been the person doing the scans at Nathan's house that we're using.
I was elected to volunteer. Yeah.
Voluntold to go scan, so we have a little use case to work through.
Yeah.
Awesome. Okay, James, quick intro from you.
Yeah, I'm James Norris. I'm the VP of Industry Strategy at ClearEdge. Before that, I started off as in surveying, but then I was in construction for a design build firm for a long time, and we ran the BDC department and did a ton of scanning all the way through like progress tracking. So yeah.
Awesome. So that's it as far as planned intros. If anyone else is on the line and wants to give a quick intro, feel free to unmute yourself. If not, and you just want to listen in, we can move along. Any other intros that want to be made?
I'll put myself out there. David Francis. I'm with ICT Tracker. I'm the CTO. My background's from construction all the way. I'm a pipe fitter by trade, got into technology later in my career. Tolerance is a real big pet peeve of mine because I've been dealing with models, and I was on the LOD committee. So that was a big dog fight on the LOD committee. What's a 300 model and tolerances all the way up to, then you start talking about prefab. And then when scanning came along and we're trying to align scan models versus BIM models, and that's just one of these things that I think the game these days is to find out what's the definition of acceptable tolerances, because concrete's not flat, steel's not straight, you know, the world is not perfect, yet the BIM model seems to be. So that's always the challenge, I think.
David, I feel like you just did an intro to the topic that we're diving into today, right? Yeah, Kelly, could he have teed you up any better?
Been watching it a while, what can I say? That's why I'm here.
I also love the element of prefabrication, because this is where we're testing how all the layering of tolerances is really going to work. So we have all these ideas and themes that we're trying, but prefab is really where we, put pen to paper and actually have to have things come together.
Yep,
All right.
moment of truth.
Any moment of truth. Any other intros that we want to go through here?
I'll say hello. My name's Brad Medlin. I'm also with Duke Energy. I work for Tom, and he's kind of like my big picture man, and I'm kind of like the small and dirty, get down in the weeds sometimes.
Hey, you need everyone to make the project built, right?
Absolutely.
Awesome. Anyone else before we dive into the subject here? Okay, so we are going to, can you guys see the, are you guys seeing my window or my desktop?
Right now I'm seeing a black screen that says you've started screen sharing. Oh,
I didn't
I just see you.
I didn't think that was the one. Okay, we're gonna try this one more time. Are you guys seeing Google Chrome?
Yes.
We are
seeing something.
Seeing a presentation.
See your slide.
Yeah.
Yep.
Perfect.
Got it.
That's what I was hoping for. Okay, cool. So Kelly Cohn is the subject matter expert today from ClearEdge, and he's going to be doing a tech deep dive specific to the conversation about layering tolerances and how do we handle these different tolerances and the problems throughout project delivery and supply chain. So I'm going to let Kelly dive in, and feel free to ask questions along the way.
Yes, seriously, because we've also got some people here that have a lot of insight into specific parts of this, and I'm going to try and talk about the whole picture, but I'm sure I will gloss over or underrepresent specifics of it just in the process of trying to get through it all. So please, dive in, ask questions, etc. So. So yeah, when we were kind of hashing out stuff for this call the other day, like I said, I think the thing that's maybe surprised some of the people on the prep call was just how many layers of tolerances there are. And, you hear this all the time, right? When the customer is, for us, when the customer, when your superintendent or somebody else on your site's like, oh, we want an as-built model that's plus or minus 1/8 of an inch. At which point you go, no, you don't actually. You really, really, really don't want that. I promise you don't want that. You don't want to pay for it. You won't be able to use it when you get it. It's a terrible idea. 99% of the time. And it's because we've got all these layered tolerances, right? So, there's kind of the just sheer tolerances that exist in kind of the reality capture process. We'll talk about some of those. Then there's, of course, the process of converting what is a point cloud to something that is an inherently abstract model representation of it. There's a whole set of things that occur there. Then you've got your conversion from that model, doesn't have to be BIM, could be CAD, but from that 3D model to the actual fabrication, if it's something that's being fabricated offsite, or the kind of fabrication and installation tolerances are of course wrapped up together if you're doing something like on-site fabrication, like cast in place concrete. If you've done prefab, though, you get on site and you've got field installation tolerances as well. And then there's all the dynamic tolerances that come into play because, of course, buildings are not static as much as we all like to pretend that they are. Which then takes us full circle back to that reality capture activity of, well, what was the thermal, environmental, et cetera, conditions when the building was actually scanned? So I think, you know, at least at the layers, that's our parfait of tolerance right there. And everybody likes parfait. At least that's what Shrek said. No, Donkey said that. Sorry. Grogu's upset. I got my reference wrong. How many people here would say that they're really familiar with all of the different kind of tolerances within a laser scanner itself? Or maybe I should say, does anybody here feel unfamiliar with that? Therefore, it's worth digging into.
I don't mind 2 minutes. Feel about it.
Cool. Yeah. So fundamentally, right, a laser scanner isn't that different from one of these things, right, that happens to be on 2 different motors, one that spins it this way and one that spins it really fast this way, right? I mean, that's basically what a laser scanner is in a nutshell. What that means is there's a bunch of different systemic tolerances that are associated with that, right? So laser scanners don't make perfect measurements. Nothing makes perfect measurements. And there's obviously like a whole range of laser scanners on the market that have different tolerances, right? On the kind of low end, you've got stuff like, at least with static scanners, you've got stuff like the BLK. Then on the high end, you've got stuff like a P series or some of the Regals, ZNF. So there's and then on the super high end on the accuracy scale, there's things like Surphaser, which good luck buying one, but they do exist. And so they all kind of range in terms of 3 critical things. So the first one is just the actual accuracy of this little component, right, that makes the measurement. So there's a laser, it shoots out. Most of them are now phase-based. There are still some time-of-flight scanners on the market. We probably don't need to go into that. But fundamentally, there's a laser. The amount of time it takes for that light in that phase to hit the object and bounce back, that's basically speed of light, distance divided by 2, figure out where that point is. But we can't measure time infinitely fast. So from a hardware perspective, there's some amount of error in the precision of that distance measurement, right? And that the good news is that's something we call statistically distributed error, which means that it's not consistent on one side or the other, which means every single point you've got plus or minus whatever that range error is, and every point will have a different error. But across all of those points, the average will be really, really close to what the actual, the perfect hypothetical measurement would be. So you've got your range error. You've also got the rotational accuracy of those 2 motors, and basically the little pieces of hardware that measure, you know, how precisely, exactly where it was pointed at the time that light left. And there's also some other weird proclivities, you know, in terms of how much the thing has turned by the time it receives the signal, blah, 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 blah. But those have minuscule impacts and aren't worth worrying about unless somebody here is fabricating something at the nanometer scale. No nanometer scale prefab for the building industry. No. All right. So you've got that rotational precision. People that have messed with total stations, you've heard, you know, 2-second instruments, 1-second instrument, 5-second instruments, things like that. That's all talking about the rotational precision of a total station. Exact same thing applies to scanners, except they don't tell us in the same way, because scanners kind of have a fundamentally different operating principle in the sense that they're constantly turning and spinning. So typically what you see when we see these kind of measurements is somebody will give us, some vendor will give us a range error, you know, plus or minus 2 millimeters at an albedo, which is a reflectance property of a material, because that range error will change depending on how bright or how dark that material is and how reflective or not reflective it is. And then additionally, you know, some people, which I prefer this, they will give you a point accuracy. and this is my favorite because I think it's the easiest thing for us to correlate just from an industry standpoint. So I'm a big fan of vendors that supply point accuracy figures, because that basically says that wraps up all of those things into a single kind of understandable error. That point could be plus or minus 3 millimeters in any direction, right? So imagine a little 3 millimeter sphere around that point. So I really like that as a metric, but point being, we've got, multiple millimeter, up to, 16th, eighth of an inch on something like the BLK, quarter inch to half inch, and on dark surfaces, even worse. That's the kind of measurement noise that we've got coming directly from just the scanning process. Now, like I said, all of those are statistically distributed errors. So we can do clever stuff like averaging 100 points in one little area. So if anybody, has played around with the Rhythm software that Philip wrote originally for doing FFFL, what they're doing is they're basically taking a disc that's the size of the foot of the dipstick, and they're taking all the points in that disc and averaging them. And so that gets them a very precise measurement, right? Because there's 100 points in that disc, and the average of those 100 points is going to be really stinking close to exactly where that concrete is. Even though any individual point won't be perfect. So this is why I always point out, don't ever do point-to-point measurements and trust them to be very accurate. Because if you're taking any individual point, you're not averaging, you're back to that plus or minus 3, 5, 10, 15, 20 mils, depending on the scanner. Yeah. Anybody want to ask questions or have a quick dive discussion on any points there?
I think it's very important to, when you're buying a scanner, just to think in terms of what you're trying to achieve. Is the high level, right? It's just, if you look at the distance of how accurate a scanner is over a distance, that's what's going to make you decide what you're going to buy. And then, if you don't want to buy multiple instruments, you think about, do you want a scanner that can get onto control or not? Or do you want to buy a total station separately? But there's things to think about. But then the tolerance of that total station, because you build, I think the concept, right, is you're building air, right? You start off with, someone goes out to a piece of land and says, this is where this thing lives in the world. And there's air already there.
Yeah.
And then it's like, and if it's an existing conditions building, which is going to your scanning, you have to scan, which you can get into, I guess, is if it's a renovation, the error Kelly was talking about within the hardware exists, plus the instrument.
Plus all the others, which.
And then that gets tied onto this error of control, which goes into what someone's modeling, which I'll let you, yeah.
James, you're unburying my lead.
So Kelly, we, in this layering of tolerances discussion, that was kind of a little bit around reality capture hardware and the capture activity itself, but that was really specific to the hardware itself, right? It had nothing to do with the capture activity. So we were just talking, each of the different pieces of equipment are going to have different ranges in accuracy and different ways that you measure that. Did I hear that correctly?
Exactly. Well, different ways they represent it in their spec sheets. Yes.
Okay. Yeah, perfect.
So the measuring techniques can be applied across all of them, but right now
how they provide it to you is not consistent.
Yeah. So this is actually
think about if you're comparing apples to apples or apples to oranges, because the two different things, the range error or the point accuracy, those two may be telling you different things.
Yeah, and I'll give a specific example because, and I will admit I'm biased on this, but the parent company for ClearEdge, TopCon, likes to provide point accuracy because they feel it gives you the complete understanding, but point accuracy is always worse than any individual one accuracy. And then people look at spec sheets and they go, well, the point accuracy of this is this, and then the range noise on the BLK is this, and it's less. And we're like, Yeah, but the point accuracy of the BLK is like 3 times worse because the rotational measurements are also 3 times worse. You know, that's like, wow.
So before we even get into the tolerances, we need to make sure we're comparing apples to apples and we're looking at what hardware we're using. And, you know, back to what James said, it always comes down to tool activity output. What tool am I going to use? That's the hardware for what activity, and what output or, you know, tolerance or measurement am I needing to do my specific, you know, task that we talked about.
Yeah, absolutely.
Cool.
And that's,
Can I ask a quick question?
Yeah.
What about the fact of how almost, well, at least in my experience, almost every scanner has different settings associated with it.
Ooh.
And as you increase, for say, resolution or quality, however you want to look at that, you slow the scanner down. But that also does affect, in essence, accuracy as well, because you're slowing the rotational movements, making the gears and everything easier to capture with.
So that's not actually why. The rotational accuracy of those measurements is almost identical regardless of the speed. The reason slowing it down on most scanners improves accuracy is they don't actually slow it down much. What they do is they multiple sample. So any phase-based scanner, when you go with a higher quality option or a lower quality option, what they're really doing is they're still capturing just as many points in the hardware. They're just they're basically averaging on the hardware rather than averaging in the software after the fact. And there's a lot of benefits to this, right? Because then the stick, you know, when you pull your thumb drive off, you can fit 150 scans on it instead of 43. But you know, that's you know, that's a nice benefit, or, you know, in terms of getting cleaner looking data. But from a hardware perspective, there's not really much under the covers that's advantageous about going slower versus going faster. The encoders, they're called encoders, that are actually looking at that rotation, that are, you know, there's something that they're looking at in there that tells them where they're at. That's going to give them just as good a result, fast or slow, typically. You'd have to be basically operating past its operating range before you would start to see any degradation on the accuracy on an encoder. But multi-sampling is a great example of phase-based scanning. You don't typically see it with time of flight, because within time of flight scanners, you get more accurate results out of the single pulse than you do out of a phase-based scanner from a single pulse. And so they never really implemented on many time of flight scanners, but now that pretty much everybody's moved to phase-based scanners because you can go much faster with them, you know, almost every scanner is at least double sampling, even at their fastest settings. You know, back when I was independent and not owned by a hardware manufacturer, the rumor had it that even like the RTC, which is a, you know, 2 million point per second scanner, is actually scanning at 4 million points per second under the covers, and it's every single point is double sampled. So, you know, I don't know if that's true or not, but it's very probable, or plausible, I should probably say. So
I think a good way to correlate that is when you talked about the total station before, right? When you talk about the 1 second, 2 second guns and understanding, it's like, you know, even though it's a 1 second gun, that's, you know, it's measured, but it's like you said, it's shooting multiple points and then taking the average of that to give you the better. So that's just the single point that you're measuring with the total station. It's the same kind of thing with the laser scanners. But I think this all really goes back to kind of understanding the scope and what the deliverable is, you know, because then as all of us have done scans over time, you kind of learn it's not just like setting it up and kind of going through. There's actually kind of an art form of how you capture that information and then thinking about how you're going to kind of process it in the back end. And so part of that learning experience that I had is like, you know, I told teams, you know, part of my teams are out there capturing, it's like, hey, it's not an X-ray machine. It's a line of sight. So make sure, you know, check your setup, making sure you're capturing everything. And I've always said, like, look, if you're unsure, then go add another spot and scan, like that extra scan, that extra, you know, 2 or 3 minutes, whatever you're using. You add the more points you have to kind of complete that picture, it's going to save you, because then we all talk about the fun part of the registration process, which is the whole other aspect of this, right? You have the actual capture, but then how are you going to go through and process it and what you're working on?
Well, that's a perfect segue, because that's the next layer, and we obviously have limited time, so I want to get to it. So yeah, registration then becomes your next kind of challenge, because just like there's no perfect measurement, there's no perfect registration. And this is an area of hot debate, but there's a couple of different mechanisms or methodologies to register scans. There's survey, survey control, traditional survey control that doesn't technically have to be on some legally defined coordinate system, but just some kind of defined control network. There's the kind of targeting, which is similar in nature, but much denser with targets typically, lots and lots of targets compared to just a couple of control points. And then, of course, there's cloud to cloud, which is all the rage and super popular. And it's the quote unquote easy button of scanning registration, except when it fails miserably, in which case then it becomes the pain in your ass button. And I love the fact that, you hear all the vendors now will say, oh, well, you don't even need to do targets or survey control. No, you can just cloud to cloud everything. And then if you look at any of their examples, none of their examples are anything like the buildings we typically scan. It's like, oh, well, here's this repeating bay, of a 300-foot long building that's got a, 30 by 40 column bay, 3 bays wide, and, it's 30 bays long or something. And you run it through the automated cloud to cloud registration algorithm, and you end up with a building that's only 100 feet long instead of 300 feet long, because it found out there was lots of good overlap between those scans that squished your building, right, by 2/3, which is always entertaining when it happens. But yeah, so that matching up of one scan to another scan, which is something that we typically talk about in terms of just the local accuracy of the registration, scan to scan. And then you've got your kind of global accuracy of how accurately are all of your scans relative to the real world conditions, right? Because all measurements suffer from chain error, right? Because since every single measurement has a plus or minus, precision issue, if you chain 100 measurements together, your potential error is plus or minus 100 times that individual measurement. Now, it never works out that bad, right? It's never 100 times worse, right? But it can be a lot worse. And it just kind of depends on how it turns out. And so this is where survey control is really important, because scanners, you're kind of, if you think about the spacing between scan stations, that spacing is equivalent to the length of your individual measurements, if you want to think about it from a tolerance or an error standpoint. So if you're spacing every 20 to 30 meters or every 20 to 30 feet, that's like, okay, that's you're taking that many measurements. Total stations, on the other hand, you can set a total station up on one end of the building and you can shoot a control point a kilometer away, one measurement, right? So the goal with setting these kind of control networks is to kind of control that global accuracy. But interestingly, statistically speaking, local accuracy is actually best achieved with cloud to cloud. You cannot get as good of local accuracy match with tying into control or shooting targets.
And I think Todd,
yeah, go ahead, James.
Yeah, I was going to say that's where it kind of lands into like, what do you, depending on what you're trying to achieve, I think Todd was mentioning prefab. It's best. It doesn't really even matter unless you're prefabbing if it's like pods inside of a room, it's best to just do cloud to cloud, because it's the as-built accurate. It doesn't really care where it lives in the world.
If it's in a small space.
If it's in a small space. The one thing we've noticed was sometimes the cloud to cloud registration would tell on the control. So large infrastructure jobs, sometimes you can find your major bus in the survey network, control network, through like I'm sure Dustin's even seen that, like depending if you're doing ground control points and tying to something,
Fun when your registration doesn't work out perfectly, and then you start turning, setting priorities, and then, oh, this one control point seems to be the culprit here.
Yeah, I've so just to kind of piggyback on what you guys are saying with the control, we worked on some pretty large projects. LAX was one of the ones that we worked on. We were trying to tie all the CTA, which is basically the entries of all the buildings. That's for arrival and departures. So we're going around and first getting an idea of where these buildings exist. And that was all done with survey control, and that was done with the survey network. And then when you start to layer in that level of accuracy and the scans that happen within those buildings, tying that in there was more of establishing more survey control just so we can get rotational accuracy. And then at that point, if we can get areas of cloud to cloud, that's what we'd use for that type of accuracy, especially if you're dealing with hoistways for elevators and you want to see where steel's located for those hoistways. You want absolute accuracy in those and that type of specification. And then the rest we can kind of do target, because at that point we just need to know where major steel pieces were columns. So I think along that lines, you have to look at like the 30,000 foot overview. What are we trying to get? And then start breaking it down into pieces at that point, just to kind of get that accuracy where you need it for the trades that are going to need the accuracy at that point. That's just from my experience. That's
back to, what kind of Kelly and James said at the beginning. Kelly said, you don't want to pay for that accuracy and that level of work for everything. You want to make sure that you're looking at where do I need certain levels of accuracy.
Oh, go ahead. Sorry.
Real quick. So everything I'm hearing though is a lot of human factor going here. This is the number one thing I hear there, because you guys, I was on a job 3 years ago, and one of my questions was, I'm assuming pretty much every machine self levels these days, but there's probably machines that don't. And I've
don't trust the ones that do, because the self-leveling instruments have way lower accuracy on their verticality detection.
Yeah, so we received scans where when they tried to register it, it just looked like someone was surfing out there. And so I think that's, when we're talking about tolerances here, you're talking about devices, and this is like a lot of things in our trade. Just because we give someone the right tool doesn't mean that person knows how to operate it. And their skill levels a factor here. I mean, it's a real cool tool, and like everything, technology is great till it doesn't work, then everyone thinks it's a pile of crap. And that's the biggest fight. You have to go back to management and explain, yeah, I know we spent $10,000 on this thing, but trust me, it's a good thing. We just had a bad day,
Yeah. Well, and I always think it's interesting, when somebody will go out and spend $100,000 on an instrument, but won't send the person to a $5,000 training.
Exactly.
It's like, interesting choice there. But yeah, and so to kind of wrap this one and bring it home, we've got, different methodologies, but I think the kind of generally accepted practice within firms that do this all the time is you should pretty much always do a hybrid registration methodology. In other words, you combine those three modes because they each have their strengths and weaknesses. Cloud to cloud, it gets you the best local accuracy, but has chain error because then you have a much tighter measurement, much larger number of measurements. But it's also incomprehensible to diagnose which one is wrong. I mean, I've got 300 scans of my house because I'm testing equipment here, and there's a half-inch bust on one corner of my house because one side is unbalanced in terms of the registration graph, and there's no way to fix it because my neighbor is there and he won't let me just scan in his yard anytime I want to, unfortunately. And so it would probably take me 2 or 3 days to go through and troubleshoot, right? How do I adjust the graph and weight each link and everything else to get that little quarter or half-inch error out? Or I could just hire a survey crew to come out and, set 4 corners and then tie into survey control and weight the survey control higher. And then boom, it's fixed. So having a hybrid registration is a great way to kind of mediate between the different strengths and weaknesses of each of these methods. You can get registrations that are super tight. Like I've seen registrations that are down to just 1 to 2 to 3 millimeters of error across all the scans, tied to global, tied to local, super tight, but it takes a lot of time. And I think, I think Thomas was talking about it earlier that, they're scanning on, super, super tight tolerances, but it costs money, time and money to get that. And if you don't need it, you don't need it, certainly. But let's jump. Oh, go ahead.
Yeah, the one way that we kind of learned this, right, was understanding the back end, the registration process itself. And so that's where we learned to do more scans. So we would kind of, I'd say, crank down the accuracy. So we were doing, we had a TX6 at Excel, and we were using the 2.5 minute scans, but we were doing more scans. And then when we actually took it into RealWorks to start the registration, we'd sample those scans down into like a 20 meter radius. And that really helps that registration, right? Because then all of us have seen it or dealt with it when the scanner picks up everything. So it could pick up a wall that's 150 feet away, but the accuracy of those points isn't as good as for a scan station that's close to that. And so that's where all of us have dealt with it. You get that fuzz, right? We had a project we were scanning some of the hangar bays at SFO, and we were giving that information over to the design team, and the registrations were really tight on that one. But then we got a question back for them going, well, there's all this fuzz around the members, like I don't know which point to pick. And I'm like, that's the accuracy of it's there. Not only is that, it's the understanding of reading that fuzz that happens. And for those who've been through the process, you don't want to see a lot of fuzz. You want to see a tighter amount of fuzz, but that comes in how you're capturing the information in the field and how you're registering it.
And DJ has once again provided a segue to the next point. I love it. This is fantastic. I do want to make one point. It's better to do that cut down to 20 meters after you register, because those points far from the scanner, even though their range is less accurate, they are much better at controlling rotation. And rotation is actually your biggest driver of error in registrations. It's not actually translation, it's rotation. So you really want to use those longer range points for rotational control, and then call them so that what you're handing somebody is only points within 20 meters or so of the scan. That way they get nice clean data. They don't see the long range data, but the long range data can still filter into the registration. So, just tossing that out there. But
Hey, Kelly.
Yeah.
Just real quick, David. Just speaking to the human error, you're right. This all comes down to who's going out there and getting the data, and how they're working with the scanner, and how they're setting up their control, and how they're setting up their targets. If you throw someone out there that's new, you better have someone with them that knows what they're doing, and get them trained, and try to figure out what you need specifically when you're out there in the field. And that's how, to be honest, that's how I learned is I broke a lot of scans because I didn't know what I really wanted. But I'm coming from the modeling standpoint. If I need to put this into to the BIM side of things after I get done with scanning. So we had a lot of trial and error. So you need to definitely get them trained up, work with the people that know what they're doing. I worked with Philip Lorenzo for years. And I learned a lot from him, and that's kind of where we started this whole process with. So you definitely want to work with someone that's going to get you to where you need on the human error side, start reducing that. Sorry about that, Kelly.
No, not at all. Great point. And I think somebody mentioned early self-leveling scanners, and I quipped, but seriously, self-leveling quote unquote scanners use an IMU for their verticality, and it's about an order of magnitude less accurate than scanners with live compensation in it. A dual axis compensator, you'll hear DAC. So anytime somebody says you don't have to level the scanner, what you need to then immediately append onto the end of that sentence is, if you don't care about accuracy. Good news is IMU-based scanners, if you level them very well first, they do a much better job. So their accuracy is relative to how level they are. So you can get good accuracy out of one, but you have to level it really well. So get really good at that if you buy a cheap scanner. Let's move on to our representational accuracy. So we've just talked about registration accuracy and the actual instrument accuracy. So we've already talked about somewhere between plus or minus 3 mils and plus or minus 25 mils, and then a layer of plus or minus 3 mils to plus or minus 25 mils. So we're already dealing with at least a quarter to a half inch of error in most cases, if not up to an inch or two of error in some bad cases. But then we get to model it. And what do we all know about CAD and BIM packages? They're design tools. They assume the world is perfect because they weren't made to document as-built conditions, right? And so this is a fundamental problem that, we're representing something that is actually a complex multi-curvature surface, best probably described by a NURBS surface or a mesh. We're representing it with a flat plane, i.e. a wall, a floor, a ceiling, whatever. So there's always, even if you perfectly model, there is going to be deviation between the surface that we've modeled or the line that we've drawn representing a wall in a 2D CAD plan and the actual location of that wall, right? This is add to it the fact that generally speaking, architects and engineers do not like walls that are rotated 0.0001264853269999123 degrees. They tend to like things 90 degrees, 0 degrees, 45. They also like them plumb. They don't like them to be modeled at a tiny, kink. So now you've got rotational accuracy of representation in plan and in section. You've got deviation between the actual surface and the abstract surface that you use to represent it. And then you have the question of how, back to human error, how accurately can one trace a point cloud? And so all of these things add error. And so I'm going to plug USIBD here again and say that they have a tool that's basically developed on the back of LOD, which I heard earlier mentioned. It's called LOA, level of accuracy. And it's a great tool for describing representational accuracy when modeling from reality capture data, whether it's scan data or photogrammetry data or somebody out there with a laser disto, doesn't really matter. But it allows you to kind of classify for each scope of work, just like LOD does, what is the acceptable tolerance or accuracy of representation based off the point cloud, right? So, typically the very tightest I've ever seen spec is 1/8 of an inch. I mentioned it earlier. That's a nightmare to deliver. It's almost impossible. Well, actually, it is impossible because we tried once and then sent the customer all of the things that would be outside of that 1/8 of an inch unless we basically brought a bunch of meshes in, and the customer then backed off to 1/2 an inch because they realized how miserable that model would be to use. But there's aside from just geometrically not being able to represent it perfectly, there's manual tracing, which is kind of your worst accuracy solution. There's a lot of extraction tools. We make some, Leica makes some, Faro has some, everybody has some, where you can select points and it will fit a cylinder or fit a plane or fit a this. Those take advantage of the statistical nature of the point cloud data. So the fact that is statistically distributed error in a single scan. I forgot to mention that registration error is not statistically distributed. So you can't mathematically average it out the same way. Well, you can kind of mathematically average it out, but it's way more complicated and less reliable. So, if you've got multiple scans, that registration has to be really tight. Otherwise, you're dealing with some potential error there introduced. This is also of note for floor flatness. Anytime you can do your floor flatness with a single scan, way better. Way better. So, there are some scanners that are kind of optimized for that. Anybody's interested, I'm happy to chat offline sometime, but try and do it with a single scan if you can. Doing an entire building obviously isn't going to work with a single scan, so you got to deal with registration error, deal with what DJ was mentioning with the fuzz, human interpretation, but yeah, representational accuracy is a challenge.
I have a question, Kelly, or if somebody wants to change. So I'm in the GC side. I'm trying to build. I have contractors outside that are not exactly the most sophisticated guys. And as you said, there's nothing that is built to exactly 90 degrees or perfectly vertical. So when you're doing these scans and you're trying to get 1/8 of an inch, like who's trying to build to that? Like it's really hard to build to that.
So go ahead. I can take
Apple.
So it depends.
Apple's trying to build to that.
Yeah, but I think it's actually depends on what the thing is. So steel, if you're doing some sort of really like where the tolerance level is very small, whether it's a structural requirement. Normally you're going to find things like steel is going to normally have that requirement of an eighth of an inch installation accuracy, mainly because things are getting mounted to it. And then those things have installation tolerances, right? So, but that's probably really, yeah, that and some sort of a super flat floor, right? For a data center. So like you're doing something with like our distribution center.
But there's national standards that dictate this. So
Yeah.
concrete plus or minus 3/4 of an inch, steel. I mean, you got camber and steel. Nothing's flat, nothing's square. So to turn around and say that you got an 1/8 inch tolerance, I'm gonna call BS on it, because I've been welding for years, and just expansion contraction of steel is an adventure. So
or even the expansion and contraction of a building. Like we were out scanning for Houston Methodist, right, for one of their downtown things, and trying to figure out the benchmarks, right, because we were shooting a neighboring building because that was the only way that we had line of sight to some other targets. And as we figured out, as the sun moves across, and this is kind of probably segue into another one of Kelly's points, but as the sun moves across, that building heats up and that building starts to move. And you go out and shoot in the morning, and then you go back and shoot in the afternoon. You're like, what the hell? I'm like an inch off. Like, what happened here? And then you're like, you just start thinking about, well, shit, it's the damn thing's moving. It's heating up, and it's moving from side to side. And how do you account for that? Not only in scans, but that even just talks about just some of your project control stuff. Those are some of the fun things that those of us have been scanning or even doing survey control. It's tough. But Carlos, to answer your question on the GC side, it's tough, and you have to figure out when to scan and if it makes sense to scan. I think it's a small number of actual companies who are actually doing progress scans as they go through a particular project, because that effort is a huge lift, and the amount of data that you have to manage and update and turn around quickly to stay with project, it's obscene.
Not just effort, the cost to that is astronomical as well.
Yeah, and you certainly can't outsource that. The cost becomes prohibitive. That's something you've got to do with other, either having the scanner on site and just having it be part of somebody's daily walk, things like that. But
Carlos, like,
huh?
I didn't know if like specifically there was something you were faced with that you're just trying to figure out how to solve, or you're just asking in general.
I'm asking in general. I mean, we're really not doing this. We're exploring different things. For example, we just bought a Trimble, a GNSS antenna for doing things. So we're moving forward with our technology stack. But I'm just hearing you talk. And for example, you provide data down to the 1/8 of an inch of existing conditions. Then the architect uses this, and the structural engineer. And then let's say they tell me that I have to hide a column, and they give me an 1/8 of an inch in between the column and the drywall or something like that. So there's already an error from the scan, and you talked about chain errors. Then, and on the DC, the column is outside of the wall, and everybody's like,
I'm saying you cannot provide a model to an 1/8 of an inch. It's literally impossible. That's what I'm saying.
Half inch is even tough.
Yeah, I can provide scan data from a single scan location with a top of the line scanner that's plus or minus an 1/8 of an inch.
Yeah,
as soon as I have to register it, I'm going to tell you plus or minus 1/4 of an inch is realistic. And as soon as you want me to model from it, I'm going to tell you plus or minus 1/2 an inch is the best.
This is where I'm going. And I think you have it on the list. It's like, okay, there is a level of error we have to manage even as we design on the CAD. And you did talk about it. It's just how is this being communicated to some of the designers? Because you guys are also not understanding these details, but sometimes the design team doesn't necessarily.
Yeah, but you know where it comes from, right? It starts with the BIM execution plan. That's where the fail is. Because they go in there to say, we're going to coordinate to 1/8 of an inch or 1/16 of an inch. So think how many hours are wasted in a coordination meeting while guys are fighting over stuff that are going, are you kidding? There's a piece of duct there. Someone's going to lean into it. It's going to lean out a 1/2 inch easy. I said, plus or minus 1/2 on BIM coordination is usually more than enough. Insulation's not perfect. All these parameters in the field that aren't perfect, yet you got some propeller head kid who's running a meeting who doesn't know anything about construction, but he's freaking going there and he's making people go over 10,000 clashes that don't really exist. That's where it starts. And then to turn around and say, okay, you need to do it in the field and scan it to make sure, not going to happen.
And back to what Kelly said at the beginning, BIM is a design tool. It's not representing plumb or, you know, material, like the nuances of a board when it gets put in place and how it may be slightly out of plumb because the studs were slightly off. Like all of these material tolerances are going to play a factor, and nothing in the model is exploiting those tolerances or showing them.
Yeah, I think that goes way back to what Kelly said before. We and David, and we've, you know, it's having conversations with project teams like, hey, the BIM model is perfect. And they're like, well, what do you mean by that? And I'm like, well, if it's a 15-foot center to center column grid, that's how it's actually modeled and what we're coordinating to. But if you go out in the field, one column base 14, 11.5, the next one's 15 foot and 3/4. You know, that's, you can't coordinate down to that super accuracy, because then, as David well knows, you try to actually prefab to that level of accuracy, stuff's not going to fit.
Yeah.
I feel like this may be a really good transition, because we did get a 15-minute warning, to BIM to fab. So we talked about, you know, the model's not perfect. We talked about that the scan to model is not going to be perfect, especially depending on if it's manual or if it's an extraction. But now we're talking BIM to fab, and that's where, you know, pen goes to paper. So Kelly, go ahead and dive in here, and keep in mind, guys, we have 15 minutes left, so we got to move a little quicker.
Yeah. So, and these, I think everybody on this call is probably more familiar with anyway. So there's a reason we weighted towards the front, right? But yeah, you know, at this point now we're into, you know, the nuts and bolts of actually making crap happen. So, you know, just because you have a perfect BIM now, you know, even if everything is perfect, okay, there's variance in fabrication. You know, there's no perfect, well, there's almost perfect fabrication, but it's exorbitantly expensive too. And so, you know, typically you've got, you know, all these shops like Blocks, or like, I guess they got acquired by somebody else, but, you know, there's all these shops that do these prefab components, multi-trade prefab stuff. They have tolerances because they can't manufacture perfectly, even in a controlled environment. You know, so that's, you know, that's just kind of comes with the territory. And that comes really from, you know, machining tolerance issues. Also just sometimes making the transition from the design model to the fabrication model. I've seen errors that, you know, crop up in that, or just things that were fundamentally impossible. You know, a great example is piping elbows in these prefab things. A lot of times the design happens with, you know, elbows with no flanges. And then all of a sudden you have a flange system, and now it's slightly shifted where the elbow is, right? It's off by, you know, 1/8 of an inch, and now it's conflicting with something else, right? And it's, you know, same thing. It's like reality is not, is both more forgiving and less forgiving in some ways. And then you've got your assembly tolerance, right? You've got guys in there welding it in the factory. No weld is perfect. That introduces, you're heating the steel. When you heat the steel and you don't heat it evenly, you can actually cause the steel to have a little bit of deformation. I mean, there's just all sorts of things that'll throw these things slightly out of whack. And then, you know, again, if it's site fabbed, all those things are true, but they're happening in a non-controlled environment, which makes them worse. And then, you know, then you've got also, you know, how well are you installing it? And that really comes down to the accuracy of the control, which can be off substantially, and then the accuracy of the human putting that thing in place. And all of those things have variance, right? So if you kind of roll those two up together, I mean, you're usually talking on the fabrication side, you're usually talking 1/8 to 1/16 of an inch variation in good cases, up to 1/2 inch in bad cases. When you get out in the field, it's kind of the same thing, probably plus or minus 1/4 in good cases, plus or minus 1 inch in bad cases, sometimes even worse. Yeah, and so, you know, now at this point, we're talking about, hey, we did the scan of this thing, and now we want to prefab for it. And by the time you get down to the point of just having everything prefabbed, I mean, you're talking about a potential for, you know, 1.5 inches to 2 inches of error, additive. Now, again, it's rarely that bad, because some things will be plus, other things will be minus. They cancel each other out. So usually you don't have a worst case scenario, but you got to realize that there's a healthy amount of wiggle room there. And then, of course, we already talked earlier about the dynamic stuff. So Probably don't need to deep dive into that, but thermal expansion, dynamic loading on the building, on the structure, will cause deviations and shifts. Also, great example. I mean, we do a lot of camber analysis pre and post pour, because of course, when you pour the concrete, that changes the structure. And then when the concrete cures over time, that changes the structure. And so you've just got all these different things, and it really underscores the importance of designing for tolerance. And then to bring it home, back to reality capture, it's really important to think about all of that stuff and what the intent is for the reality capture doing, because what you can do is optimize the reality capture for the outcome that matters, right? And so the example we made on Nathan's house is he's got this attic, and he scanned the attic and he scanned the outside. He's getting prefabricated dormers that they're going to get dropped in. And, the one thing I told him is like, well, the thickness of that roof is highly questionable because you have no way of closing the loop inside to outside. So the thing to do is demo that. Even if you demo it in one small spot, demo it just big enough to get that scanner stuck through the roof, but pick up the inside and the outside, and then, run a scan and then close that up with some kind of temporary closure, and you'll have closed your loop. And basically what you're doing is taking what was, down to registration accuracy across multiple scans, lots of chain error, and you've basically closed that loop and tied it down to where you're now back operating in the kind of near single scan accuracy regime. So you've gone from something that could have been plus or minus a half inch down to something that's probably plus or minus an eighth to a quarter of an inch. And if that eighth or a quarter of an inch matters, do it. Optimize bundles, right? If you're doing another great example is like if you're fabricating something that goes in bays, like say your curtain or a panelized curtain wall system, right? You want to have every one of the bays cloud to cloud registered together, right? Because that's going to get you the best cloud to cloud, the best accuracy on each bay. But then you're going to want survey control stitching all the bays together. And you'll treat each group of scans as like a little rigid thing that's tied into that survey control, so that each one of those bays, you're basically cutting out a vast majority of the registration error, and you really only care about relative accuracy anyway because it's prefabbed, right? But then overall, you want it to be right because you do kind of want the building to close, when all the pieces are installed. So there's ways you can kind of design your registration methodology and reality capture to get the best results possible, so that you minimize the amount of tolerance that has to be designed into the system. But
Hey Kelly, we did have a question from Thomas. So Thomas, did you still want to ask that, or did it get answered already?
Yeah, just as far as so we get around to prefab. I saw in the outline talking about the installation. You also then get into what type of equipment you're utilizing, either a total station or laser tracker for the installation layout. So like,
yeah,
if we're laying out something that just installing a slab wall piece, it may not need to be that precise. But then if we're installing a feed water heater where you have spool pieces that need to fit up with weld gap being maintained, we'll use the laser tracker, maintain that weld gap and your bevels from potential cold spring if it's a mod project. But
yeah, and that all goes back to, like you said, picking the right tool. If you've got a really tight requirement, you're going to want to go with a P-series scanner, or you're going to want to go with a Surphaser if you can buy one. You're going to want to go with something that's going to give you really, really good, clean, accurate data on the reality capture side. And then likewise for control, you're going to want to use a laser tracker. You're going to, given the control for the project is set with a total station, so globally you're probably still going to be wrong plus or minus a quarter to a half an inch. But for something like you were describing, Thomas, it's the relative accuracy. Ultimately, you want to make sure that weld gap is maintained. That's relative, so you can kind of localize to that one spot, get a higher accuracy in that one spot. But
yeah, we'll also go out and scan for something that needs to be maintained that level accuracy, after that heater is fabricated, we'll go out and scan it to see deviations between design and the actual fabrication and incorporate that into our installation plan.
And I think that's something that when we look back to the how might we question we asked at the beginning is it's, how often do you need to scan? Because if we were relying on just the first scan that was done at one state of the building before material was loaded and, tolerances have changed in the actual building materials, and then you're going to try and rely on that for fabrication with the set tolerance of an eighth of it. It's not going to work. So you need to understand, how often am I scanning? At what stage do I need to scan? What scanners am I using? So if you think you're just going to scan once and have it work end to end for all of these situations, it's not. And you have to understand where all the risk is throughout this. And that's why Kelly had said, go back and scan once it's demoed to then be able to confirm. Then you can start doing the prefab after you've kind of done that gut check.
Yeah. And the trick is just to avoid generalized statements about tolerance or accuracy altogether, right? Because that's the danger. I mean, it's the same thing about LOD, right? We've all learned the hard way over the years that you don't say, I'll deliver you an LOD 350 model. No, you specify which particular scopes, which particular subscopes, which are getting which particular level of detail, because it's idiotic to deliver a level of, LOD 350, surface for the carpet. On the other hand, it's super valuable to get LOD 350 for the, steel fabrication, steel connectors, right? So, you want to tie that back to where does the accuracy matter? You optimize the solution for where the accuracy is needed, and the solution sacrifices in other places. You'll have better local accuracy, here, but you'll see gaps between this group of scan and this group of scan and this group, and that's okay, because that's design. That's where that tolerance play comes in. But yeah, just be really specific about where you're delivering what type of accuracy, right, to the client.
So Kelly, what more would you say about field installation accuracy, or do you think we've kind of covered that conversation as well?
I mean, I think people on this call are familiar enough with it that I think we've all seen that kind of craziness, stuff. I mean, I've seen columns that are, 7-8 inches out. One of our demo exam back when we were beta testing the Verity software, which that's its purpose in life, is to check installation accuracy. We were like, there's columns missing. They literally forgot to install a column. And now we've seen that on 2 jobs, not just 1, 2.
Oh yeah.
We thought we were going to be telling people with stuff was a ½ inch out. Instead, it turns out most of the value in the software is missing.
Yeah, and I think it's important just to think about how you can manage your risk through this whole situation, because everybody has a different part to play. Because that's really what the industry still is until we can 3D print a high rise and all the subsystems within it. Through things like Dogecoin, kidding, for the power of raising trillions of dollars, whatever. But it's going to be hard. So it would be really interesting to have another conversation on just managing that risk of all that layering of that compounding problem.
I have a question for some of the people maybe more familiar with this on a day-to-day basis, but just the general knowledge of tolerances. This group seems to have a really good understanding of it. But the general knowledge, there's a lot of rework that happens. And I'm just curious if people see a lot of rework happening that doesn't necessarily need to happen because of that potential misunderstanding of it. Tolerances, that is.
So I was going to chime in earlier, but we've actually set several systems within rooms where we did demo. We scanned before the demo, we scanned after the demo. We then went in and set control points with trackers and actually went in and put an entire system. We actually mocked up the entire system, prefabbed it, took it into the room and made 37 welds in the room, and only had to cut pipe in 3 places, in X, Y, and Z. And that was it.
Nice.
And that was about 350 feet worth of pipe, all in different angles and corners, mocked up from a model. We were able to go in and show the wall bow. we tend to take those accuracies a little bit to heart sometimes. I mean, I come from the nuclear industry, so just saying that, but there are opportunities to improve. But yeah, I agree with you. Saying something's X accurate sometimes is just dumb because it doesn't make sense.
And I think to kind of put a bow on this here is you can definitely prefab from scans and models. You can, it's just understanding how often you need to scan and to what accuracy and what spot checks. And we talked about the human element, we talked about the hardware, we talked about material. You just said you've done it on a project, but how often did you scan? And did you have experts doing this? And did you have these conversations? Because if you don't, you're going to end up in a really bad spot. And you have to be educated. Like, you know, Dustin, you were saying, how many teams know all these different tolerances and know how things layer? And I think that's where we get ourselves into trouble.
If it makes you feel any better, it was the first project we ever did it on.
Nice.
We learned on that project.
Well, it's
Yeah.
the cost
A
of
lot.
material too, right?
Well, actually, when we were on a
Price
job,
versus
I know we
material
get bounced, but our Georgia Tech project, the requirements were so high that it ramped the cost up like 600 grand, and it didn't happen. Like it doesn't, like certain things can increase the cost of construction only for them to be impossible. So it's good to like catch an owner early on.
Yeah.
Yeah, that's
if they're
correct
willing,
too.
they're willing to, you have,
Pay
you have-
for it,
you have to
yeah.
understand how buildings go together to win that argument. To your point, I think what Dustin was saying, you know, it's kind of like,
But like you
Oh
mentioned,
yeah,
if you're doing
agreed.
a nuclear plant, or if you're doing a clean room, the costs are, it's more painful when you miss things, you know. A
Sure.
standard commercial building, it's no big deal. We go cut it and move it again, okay? But you know, you're buying fittings that cost $2,000-$3,000 a piece. It's pretty painful when you miss things like
Or
that.
if you're prefabbing an entire unit that's volumetric, you don't have the ability to go move the pipe.
And the tactics that we use in this course are tactics that were used in the military. I train professional fighters on the side, and we use them for training the fighters, but we've converted them into a corporate friendly environment. And so there, in my opinion, there is no short term. It's being eyes and ears and letting them talk. But over the long term, it's about building the ability to train your brain to perform under pressure. That's
Whew. On that note, that was awesome. Chad, I mean, this is definitely the longest we've just gone, and I think everyone's just mesmerized. Anybody that came on midstream that was like, "So you want me to put you in your breakout room?" They're like, "No, I'm good. I'm just gonna stay here in mental health."